Let's go over an Sn1 reaction. Now, the S is substitution nucleophilic first order reaction. So when you have got an alkyl halide, let's say CH3F, that is methyl fluoride. So the methyl group, we can represent it by R. The halogen, we can represent it by X. So when this is attacked by a nucleophile, what happens is that in an Sn1 reaction, before this one, the nucleophile gets to attack, this bond will be itself broken. So we're going to have R and X. And then now you are going to have the nucleophile to come in and attack the R group. So it can either attack from the behind or from the front. So either ways it is able to attack. So at the end now you are going to have R, which is bonded to the nucleophile, and then you are going to have X. Of course it has got a lone pair of electrons because it took the electrons in this bond. So we see that in this reaction, this is the slowest step. And the rate of a chemical reaction depends on the slowest step. And so the rate we can see is just going to be given by Rx. The nucleophile is not involved in the reaction on the first step because this one automatically breaks by itself. That is why even in the rate law expression, we are not including the nucleophile. So that is why this is a first order reaction. And so whether you increase the concentration of the nucleophile or you reduce the concentration of the nucleophile, that is not going to affect the rate of the reaction. So the rate of the reaction is only affected by the concentration of the substrate or the alkyl halide. So in this kind of reaction, when you get to form product, you are going to form two products which are going to be enantiomers of each other. So let's say, for example, if you have got a carbon which is bonded to a chlorine, this is bonded, let's say, to CH3, and then so I want to also show the stoichiometry of this reaction. This is also bonded to hydrogen, and then we have got another bond with, let's say, CH2, CH3. Now we are reacting with this. I can use iodine as the electrophile, as the nucleophile. Now this iodine as a nucleophile, at the first stage will not be able to attack this. So the first thing that gets to happen is that the bond between the halogen and the carbon is going to be broken by itself, and so this is going to take up those two electrons. So what we are going to have is a carbon which is bonded to the CH3, and that is bonded again to the hydrogen, and this is bonded to the CH2, CH3. So what will be the charge of this one? So the formal charge, carbon is in group 4. It has got 4 electrons in the atom shell. It has got only 3 bonds, meaning that it has got 3 electrons in the atom shell. So this will give us positive 1. So it has got a positive charge in this compound, right? And then we have got the chlorine. Now this carbocation that has been formed will now be attacked by the nucleophile. So the nucleophile, which is iodine in this case, can either attack from this direction or it can attack from this direction. And so whether, depending with where it gets to attack, what we are going to form is, we are going to have this carbon, of course. We have the CH3, and then we have got the hydrogen there. We are going to have the CH2, CH3, and then we have the iodine, which is attached at that point. Or we can form another product. We have got a carbon. By the stoichiometry, this is going to be swapped. So we're going to have this line here for the hydrogen, and then this one which is going in the page being here. Then we are going to have the iodine there. We are going to have the CH2, CH3. So we should be able to know the names of this compound. Alright, so getting to look at this one, how many carbons are here? 1, 2, 3, and 4, meaning that this is a butane, but at position number 2 we have got a chlorine. So the name is supposed to be 2-chlorobutane. Now we need to know its stoichiometry. So we need to know the groups of highest priority. So when you go like this in the periodic table or go down on the periodic table, that will tell you what elements have got higher priority when you want to determine the R and S configuration of this compound. So going down, we have got, of course, we have got iodine, we have got bromine, we have got chlorine, we have got fluorine. So iodine has got more priority, and then we have got oxygen, we have got nitrogen, we have got carbon, we have got hydrogen here. So hydrogen is the one with the least priority when you're talking about the R and S configuration. So when you're giving these positions, the chlorine is the only one which is here, which is an halogen. It will gain position number 1. Then I've got this one, which is a methyl with, those are alkyl groups. Now depending with how many carbons are there, the alkyl group is going to gain a number. So this one is going to gain a second position because it has got a higher molar mass. This one will gain a third position. Hydrogen is the least, so it will be the fourth position. Now we need to make sure that the fourth position is in the back, but we can see that this one is not in the back, it is actually in front. So we're going to join position number 1 up to 2, and then we go to position number 3. We keep position number 4 in the back. Of course, we can see this one is in front. So when something goes like this, this is right, this is supposed to be R configuration. But because position number 4 is not in the back, it is in front, when we have this line, it becomes the S configuration. Therefore, the name of this compound is going to be S2-chlorobutane. So same, we can now name this one and this one. So the first one on top, this will be first position, this will be second position, this will be third position. So we can say we are going in this direction, right? Now the fourth position is in front. So even when we are going in the right, this is going to be an S. So this is going to be S. At position number 2, we have got iodine. So S2-iodobutane. And then for this one, position number 1 is here, position number 2 is here, position number 3 is here, right? So the direction that this one is going, actually starting from here, going like that. Oh, this is also the same. So what I was supposed to change is not even what I changed when I was writing the reaction. What I was supposed to change is these two products. So the CH2, CH3 was supposed to be there, and then the iodine here, so that when you are given the position, this is going to be position number 1. So when you're writing this reaction, we need to make sure that the configuration is like that. We always have 2 products for an Sn1 reaction. So if you don't show the configuration, it might be not marked correct. So this one is going like this, but because hydrogen is in the front, even if this is going like this, it was supposed to be S, but because hydrogen is in the front instead of the back, this is going to be R. So this is going to be R2-iodobutane. So I've got the R configuration and the S configuration. Those are the 2 products of this reaction. So what we get to see for an Sn1 reaction is that when you are writing the energy diagram, we are first going to have the breaking of the chlorine or the halogen from the alkyl halide. So the reaction is going to proceed like this. So it's going to reach on top here, and then it starts dropping. So at the beginning we add the alkyl halide, and then we add the nucleophile, but they didn't react. We also have the nucleophile there. And then on the top here, we're going to have the alkyl halide with X. They've disassociated. And then again, this will start rising. The alkyl, this one which has remained because they've already broken. This one, the R group which has remained, is now going to be able to react now with the nucleophile, and then we are going to come like that. So now we are going to have the R group reacted with the nucleophile, and then we are going to have X alone at the end like that. So here we have got two activation energies. So I've got this energy. Activation energy is the energy from the beginning to the maximum point. So activation energy 1 here. So which is very much higher as compared to the second activation energy. The second activation energy only starts from here up to here. So you can see because the second activation energy is lower than the first activation energy, that is why the first step is a rate determining step, because that's the one where you use the most activation energy. It's the one which determines how fast the rate of the chemical reaction is going to proceed. So what we are able to determine from an Sn1 reaction is that we have got two activation energies and two peaks on the energy diagram. So the first thing that happens is that we form a carbocation where the halogen just breaks itself from the alkyl halide, and then what remains as the R group now will be attacked by the nucleophile. Now when we're talking about this kind of reactions, because we can see that we first form a carbocation. So when you have got, let's say, this carbon is attached to chlorine, is attached to hydrogen, is attached to a methyl, let's say it's also attached to an ethyl group. So first the chlorine is going to break, and so what we are going to have is CH3, CH2, CH3, and then we have got an hydrogen. This as a positive charge. We have got a carbocation, and then we have got a chlorine. So we don't want these two, because they have got opposite charges, to come and react. So for this reaction to work well, this reaction is favored in a polar protic solvent. So Sn1 reactions are more favored in a polar protic solvent, because from the polar protic solvent, those are going to be able to stabilize the ionic intermediate. So these two are the intermediates we're talking about. The ions, these two ions are going to be stabilized in what we call solvation. So what happens is that water, the negative portions of water, the positive portions of water are going to come and surround this one, and then also this one is going to be surrounded by the negative portions of water, that is the oxygens, so that they don't react again. That is why a polar protic solvent favors an Sn1 reaction. So now, how fast will the reaction proceed when you're talking about a methyl and these other substances? So when you have got a methyl group, that is CH3 bonded to a certain halogen, and we can also have a primary carbon where I've got R group bonded to CH2, okay, like that. So this is a carbon which is bonded to another carbon, so that is why we are referring to that as the primary carbon. So it's going to carry a positive charge, okay, because it was supposed to have 3 hydrogens. The other one, it is X which is bonded there, so like that. And then we can also have an allylic carbon where you have got a double bond somewhere. Now the one which is supposed to be attacked is this one, which is positive, because it's the one which has lost an halogen. And then we can also have a benzene ring. So this one also here is positive because it's the one which has released the halogen. We can also have the tertiary and the quaternary. Now when you're talking about Sn1 reactions, this one is going to be the slowest reaction, like that. So the fastest reaction is going to be this one, right? When you're talking about this. Now because I've not put this one is a methyl group. This one is a primary carbon. This is an allylic carbon. We are calling it allylic because it's a carbon that is bonded to a carbon which has got a double bond. So that is a allylic. Then you have got the benzylic ring. Now we're supposed to have also a secondary carbon where you've got a carbon bonded to two other carbons, and then you have got an hydrogen, and then you have got now the compound that has to be released, which is the halogen there. This is a tertiary, I mean a primary. So the primary is more favored for an SN1 reaction. But if we substitute this instead of hydrogen with another other group, we are going to have a tertiary carbon. Tertiary carbon is the most preferred when you're talking about SN1 reactions. This is very opposite when you're talking about SN2 reaction, because SN2 reactions they mostly favor a methyl group for the reaction, right? So this is what we can talk about when you're talking about how fast an SN1 reaction and what it gets to favor. We can also get to write another one just as a last example to see how it's going to react. So let's say we have got a carbon which is bonded, of course it has got hydrogen, and then okay we have got, let's say, CH3, and then we have got a chlorine, and then we have got CH2 CH3. Now if this one is being attacked, let's say by OH, which is an hydroxide, as the nucleophile, what is the product that is going to be formed in this kind of reaction? When you're talking about an SN1 reaction, the first thing that has to be done is that this chlorine bond has to be broken. So we are going to break this bond, and you are going to form an intermediate where we've got a chlorine, a carbon first, bonded to the methyl group there, and then we have got this one which is in the back with hydrogen, and then we have got CH2 CH3. Now this one is going to remain positively charged, so the nucleophile that is coming can attack in different directions. So it can either attack this side or this side in this kind of reaction. So the two products that are possible to be formed is we are going to have a carbon, we have got CH3, and then you have got hydrogen there. You have got the CH2 CH3, and then you are going to have the OH, which is going to be bonded here. Another product that is possibly to be formed, we are going to have hydrogen here, you are going to have CH3. Now these two are going to swap, so this CH2 CH3 is going to come here, and then we are going to have the OH here. So we should be able to know what kind of products we are forming. So let's first start with the reactant that we had. So for the reactant, how many carbons are present? We have got 1, we have got 2, we have got 3, we have got 4. I'm starting counting from here because it will give us position number 2 as chlorine's position. But if we started counting from here, chlorine will be on position number 3. So this is actually 2-chlorobutane. Now we need to talk also about the stoichiometry of this one. This is going to be position number 1, this is position number 2, and this is position number 3. So we can see that we'll count in that direction because already hydrogen is in the back. So this is an S configuration because we are going in that direction. So this is going to be S2-chlorobutane. We can as well name this one which is formed here. This is position number 1, number 2, number 3, and number 4. So this is going to have highest priorities, followed by this one and then this one. So you can see again we are going in this direction, meaning that the name of this one is going to be what? At position number 2 we have got an alcohol functional group, so that will be 2-butanol because we have got 4 carbons. But this one is going in this direction, that is the stoichiometry. So this is an S configuration, so that is S2-butanol. For this other one, this is going to be position number 1, this is position number 2, this is position number 3. The fourth group is already in the back, so the configuration is going in this direction, that is in the right. So this is going to be R2-butanol. We can also say R-butan2O as the name. So This is about Sn1 reactions, and that is how we're able to work them out.